Okay. What's up, people? I'm gonna try to do a stream on Lightning, but I don't know how well it's gonna be put together, but I'm just gonna wing it. I'm gonna give the science point of view on how Lightning works and how I'm saying how Lightning works. Basically, science is saying that lightning is when the clouds, the water, it'll be rising and turns into ice, and they'll collide, and then it'll be positively charged at the top of the cloud, negatively at the bottom. And basically, static electricity is their whole scheme behind of it. But my difference is because ether is the all-pervasive medium filling the entire realm, and it's displaced, and in the stratosphere is a conductor. So basically what I'm saying is lightning is a combination of many small things that adds up to be something amazing. It's a thermoelectric supercapacitor spark gap discharge, which science can't say that because they don't have ether, and especially when you add it as a conductor, it changes a lot of aspects of what's going on in the realm, in the world. But you see the way it ambles out up here when these big, huge cumulus clouds goes all the way up to 60,000 feet in the tropics. It hits a wall and it ambles out because water is a dielectric, distilled water, and it doesn't mix with a conductor, so it hits it. It's like it hits a wall, and it stops there. So we try to open some stuff. I'm trying to do this one thing at a time so I don't overload. We'll see how it goes. See, I want to present this. Anvil. Like these clouds, they'll go up and it's like, boom, it hits a wall. Right? And you see how much volume daylight is. It's pretty wicked. There's not enough gas volume in the world to be ionizing, like they say, or light scattering. They say the sunlight's coming in and it's scattering, somehow making all this daylight, or the ionization is causing it. But this is half of the entire room, half of the entire world. Every single day. Like, there's not enough gas produced in the world, and especially when you get up here, there's nothing in the atmosphere. At where this thing tops off at is the tropopause, and at that point you're 51,000th of an atmosphere. So between 12 miles and 32 miles, it goes from 51,000th to 1/1000th of an atmosphere. There is no gas. 1/1000th of an atmosphere, that means there's nothing there, just 1/1000th of gas, right? Like, these are real daylight images. It's hard to find real daylight images because the ones you get with balloon images from satellites, from the ISS, they all are doctored so they have a, so they all look the same. But these images, the cumulonimbus clouds, they're not doctored as much. You can see it. I mean, you walk outside, you can see it with your own eyes. Daylight is very deep. But, okay, this here, and let me go to my thing here. Let's see.
Hey, my name's Jay and you're watching Plasma Channel. Now recently I've been experimenting with static electric fields and how to turn something invisible, like a static field, into something a little bit more tangible. In the process, I got to messing around with dry ice. This is fun stuff, right? But I discovered that the fog reacts in a really, really strange way to high voltage. It's not just strange, but it's actually a little eerie. You can essentially turn...
This dude's really cool here, the Plasma Channel. I recommend subscribing to this guy. He's got a lot of really cool stuff on plasma.
a blanket of fog into a ghost drawing board and draw messages in the fog without even touching it.
I wanted to show here how once you hit a high voltage, the stratosphere, that's why it's ambling out, because through induction it's creating its own voltage that they're because ether's a conductor and it's displaced, so once you get up to that
Effect is really cool. So when I first saw this, I honestly said out loud, what? Because I didn't really know what was happening. Now at first I thought, ionic wind coming from my fingertips, how cool. But I've worked with ionic wind before, I've shot episodes about it. It was behaving just a little bit differently.
Saddle bomb, hey man. Brian Roy, hey. Low? Oh. Interesting.
Before I dig into the science mumbo jumbo, I want to show you how I did this so you can duplicate it on your own.
I will look at that in 1 minute.
And filled it with about 1/2 inch of warm water. Then I built a small plexiglass separator that I'll place on the edge, which covers up the dry ice. This allows the bubbling gas coming up from the dry ice to go around the edge and with a laminar flow spread out across the surface. A surface you can now draw on. Now in order to power this phenomenon, you're going to need a high voltage DC power supply. You don't have to use exactly as I used, but I used a mini Wimshurst generator. This guy actually puts out about 20 to 30 kilovolts. You don't need, okay, quiet, go to sleep now. You don't need that high a voltage.
20 to 30 kilovolts, that's 20,000 volts, 30,000 volts.
That you can use about 5 to 10 kilovolts, get the exact same effect. What you'll want to do is ground one of the high voltage leads to the power source and take the other high voltage lead and electrically connect it to your water. That's it. That's all that's needed. Taking our little chunk of dry ice right here, you can see the fog coming off of it, chuck it in the warm water and it'll get to work practically right away. You can see the separator doing its job, allowing that laminar flow to fill the tray. The tray really doesn't need to be acrylic, but I just have a thing for acrylic. I think it always looks amazing. Plus, it allows you to see how thick that fog is. I found that once the fog is about 1/2 inch thick, it is now good enough to scribble on.
You see the way that dielectric water will not mix with high voltage.
Wind might play a component. Here's why I think there is a lot more to the story. First, most of the time, ionic wind tends to be messy and doesn't form laminar flow in free air. These fog tracks, more often than not, are very distinct, sharp lines. In particular, this track was a defined, hair-thin line emanating from my fingertip, from over a foot away. That's not messy. Second, it was a stream which always bent down to meet the fog at a perpendicular angle, no matter where I pointed, even if I point horizontal. And third, if it was a form of wind, then why isn't any of the fog blown away? Here's an example of ionic wind when I get too close for perspective. The fog is blown away. So ultimately...
Okay, that's a visualization. Let me look at this. Mic, let's see. It's turned up all the way. Okay. Well, that might be, I do see, all right, well, we'll just have to deal with it for right now. And when I look back, if it's really bad, I'll redo it or something. But bookmarks. Yeah.
This may be.
This is another video we did. Lord Racer, hey man.
Isolated container is filled with a uniform layer of fog and then given sufficient enough voltage, something fascinating happens. I really hope this is showing up on camera. This interesting little effect is something I discovered a few years ago while experimenting late at night, hopped up on a bit of bean water. I shot a video on the topic, and since then, the exact science behind this phenomena has really haunted me. It's haunted me so much that I knew I had to dig deeper, gather opinions from other professionals. This includes a large flat container filled with warm water, lots of it actually, a physical separator on one side that has a gap at the end like so, a piece of dry ice, and a low current, high voltage DC power supply. This 20 kilovolt battery powered Wimshurst is ideal because, as you can see, totally harmless. The electrical ground is attached directly to the water and the high voltage positive to your body. The key here is low current, less than a milliamp, which is completely safe in this application. Now, as for voltage, I found anywhere from 5 to 30 kilovolts works great. Once the dry ice is dropped into the water, the separator allows the CO2 fog to flow throughout the container, forming a uniform sheet. And at this point, the power can be turned on, and the magic starts. The trails range from hair-thin to somewhat thicker, as seen here, and even really wide, unpredictable bursts. Actually, quite unpredictable. Your finger can draw on the fog from over a foot away. It really is something beautiful. Perhaps the most intriguing of all, though, a flat palm placed just over the fog. Oh my God. Creates a clear vortex.
That's amazing right there. It's almost like a hurricane or whatever. That could be good. Woo! Makes a vortex.
As you saw, this setup in essence acts like an actual drawing board, and
Okay. I just wanted to show how, because the stratosphere is this conductive area and daylight is making its own voltage through induction up there, that the clouds do not mix with the stratosphere, so that's why it like hits a wall and then ambles out. Like, I don't think science has an explanation for it, unless if they do, it's probably gravity, I would say. But okay. Yeah, bookmarks. Yeah, I'm doing this one tab at a time, so it's very impromptu and throwing this together. So, lightning itself, like I said, it's a thermoelectric supercapacitor spark gap discharge. The thermoelectric effect. This thing is when you have a temperature differential. Like, this is two conductive plates with a dielectric in between. And the two conductors is the stratosphere. The other conductor is the ground. And then in between the dielectric is your air and water. The dielectric breakdown, dielectric strength. Let's see. Pull these things up. Sitting in the sun, saddle bum. What do you mean? Is it nice where you're at right now? Is that what you're saying? Yep, no, wrong one. Okay. Distilled water. The dielectric strength. So it takes this many megavolts a meter. It takes 65 to 70 to get through distilled water. And then versus just air is 3. So let's see. Dielectric strength, atmospheric. Field data. Yeah. The thermoelectric. This because on the Earth's surface it's 60 degrees in the tropic, but way up here at the stratosphere it's -60. the science can't apply this. They can't do thermoelectric because they don't have the stratosphere as a conductor. They won't apply this. They're doing static electricity, like these ice particles clashing, colliding into each other. When I went over briefly at the beginning, and I'm just flying through this. I'm just trying to get this out, and it's definitely not. It'll be something I'll have to go over again. But the thermoelectric is what we're doing right now. How this is such a huge role in lightning, that you have this temperature differential, negative 60 and 60 on the ground. And this is the tropics. This is why you never see lightning in the winter. You will never see lightning storms in the winter because it's already cold on the ground and cold in the air. Like in the tropics, you have 120 lightning strikes every single second. Okay? And it's all in the tropics. Let's see. Oh, am I even... Oh, no, I ain't got that. Oh, man. Oh, boy. This is what I need to do. Yep, I'm already getting off to a bad start because we can't see any of this data I'm putting up. Ooh, okay. Yay. Yay. Okay. This here, the temperature, sea level 60 degrees. At the tropopause, negative 60 degrees. This big temperature differential, because as you go up in the atmosphere, it gets colder and colder and colder. See, and this is data from the stratosphere. I'm just going to leave this on full screen instead of that by the tab. All right. And I had, what was I showing before? The dielectric breakdown. This other table I had distilled water right here, 65 to 70 millivolts a meter. And then air 3. So basically, okay, pull this up. Okay, you can still see all this. Yeah, you've seen this. The thermoelectric. I'll show you some more of what thermoelectricity is going to do. Bookmarks. So you already see here, it's hot on the bottom of this. There's a conductor, a dielectric in between, and another conductor on top. So this is the stratosphere. It's cold. You got ice up here, and then you got the dielectric, which is going to be the air, distilled water, and then you got the other conductor, which is the earth, or surface, or earth, whatever. And it creates a voltage. Here's another example. It goes into this water, and you're already getting a voltage. It's making the fan go. He throws some cold ice water on top, and voltage increases so much more. Here's another same thing, thermoelectric effect, and this works both ways. You can also apply a voltage, and then it'll create a it'll make one side of this Peltier module hot and the other one cold, like those little mini fridges that you have in your cars. They use these little things to make them cold in the fridge. Alright. see. Ooh, boy. There's so many things. There's always a bunch of little things that adds up to be something amazing. Okay, well, buzzes are. Heron, hey. Dr. Bass Ackwards, what's up, man? Good to see you. Let's see. Let me read this comment. I don't have a good explanation for when we see the sun low on the horizon and it appears below the clouds. Even though it's not below the clouds, how can the sunlight shine up underneath the clouds? Well, the horizon is where the sky apparently meets the ground, and then the clouds are going to be up in the sky, so the sunlight is shining from the bottom of the clouds. Like, if you're on a globe, I don't have any visual demonstrations of this, but it wouldn't be possible. Like, you would have to go through the clouds, and then you got to go through the clouds and then back up through the clouds again. It doesn't make sense at all. But it makes perfect sense on an infinite plane. Like, that should be one of the main, like, another main proof that we live on a plane is because of that, because you could see the light through the bottom of the clouds, especially when you see like those mountains where the cast a shadow across the entire sky, where if it was a globe it wouldn't do that. Ooh, driving. Yep. Okay. Yeah, I mean, I understand it mentally how it works on an infinite plane, how the sun is going, because the horizon is at eye level, but the clouds are up in the sky. Yeah. So thermoelectric, right? You have this temperature differential. Where in the tropics, which is where all the lightning is taking place normally, and until we get summertime, and then we'll get lightning and stuff, the thunderstorms when it's hot on the ground and cold in the sky. But when the sun moves down and it's winter up here, you will never see a lightning storm in the winter because it's cold on the ground and cold in the sky. You would think that according to science, with the way they explain with the static, that you would have lightning all year round if it's just ice crystals knocking into each other, making all the static. But no, it's thermoelectric. That's one of the main factors of lightning, is the temperature differential. And I was showing you how these thermocouples, where are Peltier modules, where you have two conductors, and one conductor being the stratosphere and the other conductor being the ground, that is going to make, and then the dielectric in between. And like, everything in existence has an electrical breakdown. Glass, everything. It just, the breakdown of the electric is more and more, like, glass is a one-time use. Basically, once you break down glass, it shatters. It's just a one-time use thing. But you need more and more voltages based on different resistance of materials. Like, air is 3. If I could, wish I wouldn't see files. Yeah. What do I got here? I ain't gonna find this in here. Files, images, bunch of same stuff. I have my own little, well, where is that file? I have a 12,000 volt ionizer module that I showed the breakdown of air. Oh, here it is. Like, it takes so many volts to get, like, air. This is air just in my bedroom, standard pressure and temperature. And it takes 3,000 volts per, well, it's 30,000 volts per centimeter. Let's see. Trying to get this right. 3 megavolts, kilovolts. Yeah. So it'd be 30 kilovolts. A centimeter is the same as 3 megavolts a meter. Anyway, show this. If you were to separate and move these further apart, it would take more and more voltage the further apart you moved it. The closer you get it, the more it would break down. So let's watch this. This is about 1 inch apart. That's dielectric breakdown of just air. But if you were to do water, you would need a lot more voltage to break it down, to turn it into a conductor. It's pretty strong. Anyway, so thermoelectric. Definitely not as organized as because I am doing this on the fly. All right, bookmarks. Check the comments. Jeremy Bird, hey man. Yep, for sure. Legends in the chat. Yep. Lord Racer's been around forever. Heron, Dr. Bass Agwards. I don't know. Yeah. Glad to see you guys. Capacitor. Now, the supercapacitor. I was telling you how it's a supercapacitor. Well, the way a capacitor is 2 conductors and a dielectric in between. See, a dielectric. So we're talking about the ground, the stratosphere, and then this is the air and the distilled water. The distilled water has a much higher dielectric breakdown. And that's what's making it turn into a supercapacitor. A normal capacitor typically only uses air. Normally, these things just use air, but there is different materials they will use as the dielectric. But whenever you have distilled water, that is 20 times higher than air. So that's all the capacitor is. So you got the thermoelectric, 1 cold, 1 hot. You got the capacitor, which is a dielectric, and 2 conductors. So yeah. So thermoelectric supercapacitor and spark gap discharge. And I just showed you what a spark gap is just the breakdown of air. But so and with the earth, we're reverse engineering everything. Like, we don't do wires. The ether is the wire. The ether is the conductor. And I don't, if you watched any of my other streams, basically the atmospheric pressure, atmospheric field data, the pressure, atmospheric pressure, all this at sea level, 1,000 millibar. At 3 miles is 620. At 12 miles, it's 120 or 50. And then at 32 miles, it's 1 millibar, 1/1000th of an atmosphere. So there's more resistance in the air. There's water in the air. There's dust, like biological matter floating around, like tree bark, whatever, in the air. There's all this resistance. And as you go up in the atmosphere, it's less and less resistance, and it becomes more and more of a conductor. And by the time you hit the stratosphere, it's a pure conductor. So, plain and simple truth, hey. Yeah. Having a good Friday. Yeah. Trying to get all these things out. Man. It's pretty ridiculous. But yeah, when we're reverse engineering, you got to think outside the box. Like, the ether is a conductor. The stratosphere is a conductor because, well, at the between 12 and 32 miles, you're at 51,000th to 1/1000th of an atmosphere versus all this resistance at sea level. There's ether down here, but it's being displaced by different molecules, different matter, and things that's in the air. Like, there is tons of water in the air, like, and gas and all that. And these molecules, like, moves the ether out of the way, right? There's a lot more pressure down here pushing this ether out of the way until when it gets to the stratosphere, it's a pure conductor. And I love Kung Fu. Hey, man. I'm glad. It's good to see you guys. Glad you stopped by. So a thermoelectric supercapacitor, and then spark gap discharge. So we kind of understand what a capacitor is. We understand what thermoelectric is. And this is like totally way off from what science is saying. And this is shown, this is like real stuff that's going on. Like, that really happened. Thermoelectricity. Alright? Like, capacitors. And they can't apply that because they have a model where it's goes in outer space. Like, the further you get away from the ground, the they call it free space or black matter. Like, at the 12-mile mark, or say you're at the 32-mile mark, 1/1000th of an atmosphere. Well, one, all this gas is like spreading out. There's all this space in between the gas, right? There's, they call it free space or black matter, but in the realm, it's ether that's the all pervasive medium filling the entire realm. And it's a conductor, so that flips everything on its head, and all this other stuff going on that science can't attribute because they'll never say ether exists. They'll never say it's a conductor, right? They'll say it's just free space. They don't know what it is still, because these molecules are spread out. The farther you go up, they spread out and out until you get to outer space, and then you eventually get to 10 to the negative 17 torr in the middle of the whatever, the void out there in outer space. But I'm saying that it's a closed system, right? Like contained, whatever. And ether is what is in between all these little molecules, even all the way down here on the ground. It's just being displaced as it goes up. But let's see, what is my next thing? My last stream, I posted about how it acts like a tank circuit in the troposphere. And this here, this is the capacitor. The capacitor is the air in the clouds, the spark gap discharge. This is the lightning. And then up here, the primary coil, that's the inductor, an RLC tank circuit. A resistor, which is the resistance, is the dielectric breakdown of air. The inductor is up here, let me see. And then the capacitor, this is the capacitor. Right, this is just the troposphere. All these, like, reverse engineering this, you have to think like outside the box to understand this. And then this here, the secondary coil, is the stratosphere. Like, we don't do wires, it's ether instead of ether is the conductor, not the wires, not the copper wire. But the lightning is this, let's see, 12 minutes, I think. Yeah, this is not connected to the primary coil at all. This secondary coil is connected to the ground, and it makes a circuit from the ground around through here, but it resonates off of what this primary coil is doing. But what it's showing is that through induction, you can have a moving magnetic field through a conductor or you can have a moving conductor through a magnetic field and it'll create a voltage. But whenever you bring a fluorescent bulb up close to it, you'll see it lights up the bulb, because this magnetic field is moving through a conductor. It's induction. And in a fluorescent bulb, this is a really low pressure state. They remove all the resistance out of fluorescent bulbs. So as the field's moving through it, the magnetic field, it's creating voltage. This here is induction. You can have a moving magnetic field through a conductor, which in this case with the realm, the conductor is ether, not copper wires. But you can have a moving magnetic field through this. It's going to create voltage. It's going to turn the light on. It's going to make voltage. Just a moving magnetic field. Or you can hold the magnet still and move the conductor over the magnet, and it'll do the same thing. It's two-way, just like the thermoelectric effect is two ways. You can have a temperature differential that's going to make voltage, or you can apply voltage to the two conductors and it'll create a temperature differential. That's how those little mini fridges are cooled. They use Peltier modules, and they use them in some computers too to cool electronic parts. Those little modules, you could freeze water on the things just by applying voltage to two conductors with a dielectric in between. All right. Just throwing some of these out. So he'll show you again. He's going to take this is conductor, just wires. And he's going to move this magnetic field through it. It's going to create a voltage. It's induction.
इसके करीब रखा मैं मूव नहीं करवा.
Okay, just moving a magnet and it's making a voltage. See that? That's amazing, right? Through induction. Or he could do the other. He can hold the magnet still and move this copper wire up and over. It's going to do the same thing. You check out for the comments. See, I don't understand that question, Saddlepalm. You're saying, you're talking to Brian? Oh, okay. Regarding your sunlight under the clouds question, portions of my walls and ceiling are lit with no direct sunlight coming through my windows and sliding glass door. Yeah, they say there's no ether, but then we have technology like wireless point-to-point Ethernet data transfer. Yeah, I mean, they do call it Ethernet because it's all instantaneous. Like we're doing all this right now. If I had somebody chat with me, they could be in South America. Like I could be talking to Flatzoid instantaneously, and we're using radio waves to go from like my laptop to the router. That's radio waves, and then the router is going to use a friggin' coax cable, another conductor, electricity, and send it through to the servers, and then the servers is going to send it through fiber optic cables all the way across the ocean. And then that'll hit some more servers, and then back again in 0.3 seconds instantaneously. So we're using all the electromagnetic light. We're using radio. We're using electricity. We're using all these things, showing that it's all instantaneous and it's all instant, which is amazing. It's Ethernet. Right? Like, I saw a cool documentary last night about how photosynthesis is BS and trees are actually growing as a result of light turning into matter. I see light as voltage. But yeah, I used to do a lot of horticulture, and I would grow indoors, and I started out with high pressure sodium lamps, and then I moved into LED, which LED, um, it's different. It's like cold light. Like the high pressure sodium is really hot, but they consume the same amount of power or wattage. So low voltage, high amps, or high voltage, lower amps, it's the same amount of power. But yeah, I think that definitely worth a deeper dive into photosynthesis. But yeah, maybe I put a link in here in song. I'll take a look at it if you find it. I'll give it a deeper look. I get into spectrography. There's a lot of like questionable things about light that I wonder about myself. Let's see. Yeah. Right now I have Discord set up. Sometimes I use Google Meets. Right now I'm using OBS, so I'm trying to integrate that somehow. Let's see. My Discord right now, I got just using this. Just made my own channel. It's really simple. Flatzoids, I got Fed, Nathan Oakley's, a bunch of other flat earth. Roger, got Roger's server on here. He's got to fix that thing. Politics, 24/7. Yeah. Anyway. So if you do have Discord, it just pop you up here. You just go to voice chat, join it. Yep. Yeah, sometimes just texting is very difficult to get some of your points across. Okay, here. Yeah, light's really cool. I plan on doing some things on light. A stream on that. Like Moonlight. I don't know if you've ever seen the hotspot through the clouds, but I'm here on the East Coast of the United States. And at any given night, at the exact same minute, the exact same second, somebody on the West Coast will have their own hotspot in the light. It's independent and unique based on where you're at. You know what I mean? Like I got my hotspot, somebody in California will have their hotspot at the exact same moment, which is very interesting, right? Like rainbows, they're polarized, but a prism is not polarized. And the electromagnetic spectrum, they have frequencies for all the lights, all the Roy G. Biv, but not white light. Like, that don't make no sense to me. Like, right? And the way that they say photons work, at 1 minute, science will say they're photons, and the next minute they're waves. When you do a double slit experiment with laser lights, they use them interchangeably whenever it's convenient for them, or they'll call it duality. But when it comes to ionization, like they're saying with the daylight, in that case they're photons, which I would debate any science person on that. Photons, ionization, the basic principles of what they say light is or whatever, it makes absolutely no sense. They're saying like electrons are knocking into each other, and then that excites them, and it'll shoot out a photon at the speed of light, apparently. But these photons individually are individually colored. Like it could be a purple one, it could be a blue one, or whatever. And then these photons combine together and make white light. Like they bunch up together. That's how white is made. There's not one particular white photon, they say. So I have a lot of problems with that, especially ionization. And there's a lot of falls with that. Oh, really? Man. Okay, I'm going to have to work on that mic issue, man. And I need to do a better job at consolidating and having all this stuff a little more put together, because I'm trying to throw all these things in at one time and trying to get it across impromptu. Yeah, it needs to be a little more organized. So I'll work on that. And my mic. Let's see, with my mic right here, I'm getting mic check 1 2. Yeah, it is low. It is low. That is weird. Usually it's hitting red. That's very awkward. I'm at to work on that. Yup, it is low. Okay. Wow. Yeah, light is energy. Yeah. Light's amazing. And then there's the opposite, where when you see objects colors, it's the absorption. Like what they're absorbing and the colors that you see versus the actual light itself and the colors that they're making. Dang. Okay. Well, my mic's that bad. I'll have to do another stream. And Flatzoid's on in like 20 minutes, so I'll probably just end it here. And if you can't find it, Heron, that link, you can just text it to me and whatever. I'll give it a look. But yeah, I gotta work on this mic, so at least I got some of these points across, and if it's that terrible, I'll just redo it again or elaborate on some of these things or something. So you're gonna need a minute to find it, Heron. I guess you could just text it to me. And today's Flat Earth Friday on Flatzoid's channel, so I'm gonna go over there and talk to them. Yeah. All right, guys, I'm gonna end it here. Now figure out this mic thing. What? That's weird. It's usually loud. Okay. Play this song, and I'll see you guys later. Thank you everybody for stopping by. It was good to see you. Thanks for stopping in, and I'll see you guys soon. See if this plays, and see you later.